Hello everyone. Today I'm going to talk about the Alon Tarsi number of planar graphs. Okay, first I will define what is the Alon Tarsi number of a graph. A digraph D is Eulerian if each vertex has in degree equals out degree. We do not require the digraph to be connected. Right? For example, if the digraph has no arcs, then it is Eulerian because for each vertex the in degree equals out degree equals 0. Okay. Assume D is orientation of a graph G. We denote by ED the family of Eulerian subdigraphs of D. So each Eulerian subdigraph is a spanning subdigraph of D that has each vertex in degree equals out degree. We will treat each Eulerian subdigraph as a subset of the arcs of D. And we use EED to denote the family of the Eulerian subdigraphs with an even number of arcs, and the EOD those with an odd number of arcs. And the difference D is just the number of even Eulerian subdigraphs minus the number of odd Eulerian subdigraphs of D. And we say D is the orientation, D is Alon Tarsi if the difference is not 0. That means the number of even Eulerian subdigraphs is different from the number of odd Eulerian subdigraphs. Okay, assume F is a mapping which assigns to each vertex a positive integer. We say the graph G is F Alon Tarsi if there is Alon Tarsi orientation D such that the out degree of each vertex is at most fv minus 1. Now, if k is a positive integer, we say G is kat if it has orientation with maximum out degree at most k minus 1. The Alon Tarsi number of a graph is just the minimum case that G is kat. Okay, so G has an Alon Tarsi orientation with maximum out degree at most k minus 1. Okay. So the Alon Tarsi number is very important graph parameter because of this theorem. So this theorem is proved by Alon Tarsi that every graph, for any graph G, the choice number of the graph is bounded by the Alon Tarsi number. Okay, so this was proved by using the combinatorial non-standardizers, and this is now a very powerful and useful tool in the study of least squaring of graphs. Okay. This is a classical result now. Thomason proved in 1995 that every planar graph is 5 choosable. And then a natural question is that, is it true that every planar graph has Alon Tarsi number at most 5? And Alon Tarsi number is upper bound for choice number, and this difference can be arbitrarily large. So this question was asked by Herfis in 2011. And this question, the answer is positive. I'm going to show you today that every planar graph has Alon Tarsi number at most 5. Okay, let's first prove this theorem. And the proof is very much similar to the proof of the 5 choosability theorem by Thomason using induction. And we have to find the correct statements to be proved by the induction. So assume G is a plane graph and E is a boundary edge, and F is a function that assigns to each vertex a positive integer. And this integer is defined as follows. Say this is a special edge, special boundary edge. The end vertices of this boundary edge, they have value 1, and other boundary vertices, they have fv equals 3, and for each interior vertex fv equals 5. So this is a function that we're interested in, and the theorem we're going to prove is that for the function defined as this, the graph G minus E is FAT, so has an Alon Tarsi orientation such that the out degree of each vertex is bounded by FA minus 1. Okay, so this, if you compare this result with Thomason's theorem, Thomason proved that G minus E is F choosable. They say this, what it says is V1 and V2, they are pre-colored, so they have list size 1. That means it's already colored, and each boundary vertex has 3 permissible colors, and each interior vertex has 5 colors, and then you can color it. This is Thomason's result. So this is parallel to that one. Again, we're going to do this. Okay, so this is what I said. So if you remove this HE, you can find the orientation so that for every vertex, the out degree is the most FV minus 1. The out degree condition is that this one, say this one is 0, that means there's no out degree. This is 0, there's no out degree. Remember, this edge is going to be removed. It's not going to orient it. And interior vertex, the out degree is at most 4, and other boundary vertices, the out degree at most 2. So that's the out degree condition. And usually this condition is easy to be verified, and the other condition is that it has to be Alon Tarsi orientation. Alon Tarsi means that the difference is not 0. The number of even Eulerian subdigraphs is different from the number of odd Eulerian subdigraphs. Okay, so we consider 2 cases. If you remember Thomason's proof of the 5 truthability for planar graphs, that is very similar. So the first case is that if there is a chord, the boundary cycle of the graph has a chord. Okay, in this case, okay, so the chord separate the graph into 2 parts, G1 and G2. We first apply induction to this G1. We get the required orientation. This is orientation of G1 minus this edge, which satisfies this out degree condition, and which is Alon Tarsi. Okay, the out degree condition is just this F1 is just restriction of F to the vertices of this part. And then we apply induction to this D2, and this orientation of G2 minus this edge. Now this edge plays the role of the special edge on the boundary, and such that it satisfies the out degree condition, and it's Alon Tarsi. Now this out degree condition is that this vertex has out degree 0, because this is special edge, and every other vertex, boundary vertex out degree at most 2, and this interior has out degree at most 4. Okay, so once we have this, we just put the 2 orientations together, 2 digraphs together, D1, D2. This is orientation of this G minus E. So we write the union, just simply treat D1, D2 as edge set, arc set, or arc set. Okay. So this is orientation of the graph G minus E. So every edge, including this edge, it's get an orientation, right? This edge is oriented in D1, but in D2 it's not oriented. D2 is orientation of G2 minus E prime. Okay, every edge get orientation, and it is easy to verify. The out degree condition is satisfied, including these 2 vertices, right? These 2 vertices in D1, they has out degree at most 2, and in D2, they has out degree 0. So altogether, they still has out degree at most 2. So out degree condition is easily checked. And it is also an Alon Tarsi orientation. That means the number of even Eulerian subgraphs is different from the number of odd Eulerian subdigraphs. Now, why is that true? Okay, so we look at this arcs incident to these 2 vertices, because these 2 vertices has out degree 0 in D2. That means all the arcs in D2 incident to these 2 vertices are pointing towards it. They are in arcs of these 2 vertices. So you look at this card. Okay, this is a directed card. All the arcs are going from left to right, from right to left. Okay, so then none of this arc is contained in a directed cycle, right? Because there's no way to go back. But we know that the Eulerian subdigraphs, the arcs of Eulerian subdigraphs, can be decomposed into the arc disjoint union of direct cycles. That's easy to see. And but these arcs are not contained in any direct cycles, so they are not contained in any Eulerian subdigraphs. Okay. So then, if these arcs are not contained in any Eulerian subdigraphs, then what are the Eulerian subdigraphs of D look like? How they look like? Okay, they all of this form. You take an Eulerian subdigraph of D1, take an Eulerian subdigraph of D2, and put them together. So again, I treat this is an arc set, this is an arc set, and put them together. So this is an Eulerian subdigraph of D. Okay. And all the Eulerian subdigraphs of D are of this form. Now, if these two digraphs have the same parity, that means if they are both even or both odd, then this is even. And if they have different parities, then this is odd. So therefore, we get this inequality. You look at what are the even Eulerian subdigraphs of D. That is, you take an even Eulerian subdigraph of D1, take an even Eulerian subdigraph of D2, put them together. Okay, just side by side. Then you get a Eulerian subdigraph of D, which is even. Okay, then you can take an odd Eulerian subdigraph of D1 and odd Eulerian subdigraph of D2, put them side by side together. Then you get an even Eulerian subdigraph of D. Now, similarly, you have this inequality. You take even from D1, odd from D2, or odd from E1, even from D2, you get odd Eulerian subdigraphs of D. So you have this equality. From this, it is easy to derive this equality, right? Just multiply this out, you got this. Okay, it's easy to verify it. And because both difference of D1, difference of D2 are non-zero, this is non-zero. So this proves that D is Alon Tarsi orientation. Okay, so this finished proof of the case 1. So if there's a chord, then we're done. The case 2 is that there's no chord. Then we look at neighbors of Vn. Okay, this is again similar to the proof of Thomason's proof of the 5 choosability of planar graphs. Okay, so we delete this Vn. Okay, get a subgraph G prime. And G prime, this boundary, this is the boundary of G prime. Okay. Observe that these vertices are interior vertices of G. They are not boundary vertices of G. If they are boundary vertices of G, then you would have a chord, but that will be in case 1. Okay. So now we apply this induction hypothesis to the smaller graph. We get an Alon Tarsi orientation of this subgraph, which satisfies the boundary, satisfies the out degree condition. Okay, then we extend this orientation D prime to an orientation of G minus E. So this is orientation of G prime minus E, not G, it's minus E. They extend it to orientation D of G minus E. How do we extend it? We just need to orient the edges incident to UN. Okay. The extension is like this. So these neighbors, the arcs are pointing from U1 to Vn, U2 to Vn, and so on. And then these two arcs are out arcs of Vn. Okay, so this is the extension of D prime to D. Okay, for this D, the out degree condition of D is correct. Right? So this out degree has out degree 2. That's okay because boundary vertices other than V1, V2 can have out degree 2. And this vertices as out degree, it was out degree at most 2 in D prime, and now it's at out degree at most 3. So that's okay. They can have out degree 4. So the out degree of this vertice are not changed. Other vertices are not changed. So the out degree condition of D is satisfied by this orientation. Now, if the Alon Tarsi orientation is also satisfied, if this is Alon Tarsi orientation, then we're done. Okay. So thus we may assume this is not an Alon Tarsi orientation, which means that for this digraph, the number of even Eulerian subdigraphs is the same as the number of odd Eulerian subdigraphs. Okay. Okay. Now, what are the what are the Weyl subdigraphs of D? First of all, every Weyl subdigraph of D prime is a Weyl subdigraph of D. Remember, so when we say Weyl subdigraph, we always assume, like, we view it as a subset of arcs. Okay, so if it's a Weyl subdigraph of D prime, and then these arcs are not there, so Vn has integrate 0 and outegrate 0. So it's isolated vertex in that Weyl subdigraph, but it's still a Weyl subdigraph of D. Okay, besides those Weyl subdigraphs of D prime, there are some others. What are the others? Those new Weyl subdigraphs must contain some arcs incident to Vn. Okay, but this arc cannot be contained in Weyl subdigraph because it is not contained in any directed cycle. This is a sink. Okay, V1 has outdegrade 0. So this arc cannot be used in any Weyl subdigraph. And this arc must be used in a new Weyl subdigraph. If this one is not used, then none of these can be used because the outdegrade is 0, the integrate has to be 0. So this one has to be contained in any new Weyl subdigraphs of D. And this one, that means this vertex has outdegrade 1, no more, no less, exactly 1. And then it must have integrate, it must have integrate most exactly 1. That means one of these arcs is going to be in the Weyl subdigraph, exactly one of them. Okay, exactly one of them. Now I use AI to denote this arc, and I use EDAI to denote the set of Weyl subdigraphs containing this arc, and the even ones, that means with even number of arcs in this set, and the odd ones. Okay, so now, every Weyl subdigraph of D is either a Weyl subdigraph of D prime or is something like this. So therefore, the even Weyl subdigraphs of D is the even Weyl subdigraph of D prime union this, and so we have these two equalities here. So these are disjoint unions. Okay, so this does not contain AI. If it contains AI, then it does not contain AJ. So they are disjoint. So therefore, the sides is just the summation of the sides of these sets. Now we know that D prime is an Alon Tarsi orientation. That's by assumption. That means these two numbers are different. Their difference is non-zero. These two numbers are different. And we assume that this is not Alon Tarsi orientation. That means these two numbers are the same. Okay, that implies some of these AIs, the even ones, even Weyl subdigraphs containing AI, is different from the number of odd Weyl subdigraphs containing AI. Okay, we choose one, fix one. So this is the one. This is the one. The Weyl subdigraphs contain this arc. So if it contains this arc, then it must contain this arc, and then it must contain a directed cycle. So each arc in the Weyl subdigraph is contained in a directed cycle. So there must be such a directed cycle. Okay, there may be many such directed cycles, but we fix one, just fix an arbitrary one. So this is a direct cycle containing this arc. Okay, now we're going to change the orientation D. So how do I change it? This is the new orientation. I take this directed cycle, but do not take into this edge. So this is my C minus AI. Take this part, remove it, and then take the inverse of this. Just reverse the orientation of each arc of this path. This is the reverse, I think. Okay, and so I put this back. Okay, remove this. That means remove this, add this, reverse. Okay, this is my D double prime. Okay, now I'm going to show this is the orientation that is we're looking for. First or the out degree condition is correct. Okay, so this out degree is 1, that's correct. It's at most 2, that's okay. And the out degree of the other vertices are not changed except this one. This was incoming edge, but it becomes outgoing edge. So this out degree increased by 1. So in D prime, that means in the orientation of this graph, the out degree is in most 2, because it's a boundary. There's a boundary vertex. And now it has 2 more new outgoing edges, so the out degree is most 4. But that's okay, because it's the interior vertex. It can have out degree 4. And so the out degree condition is correct. Now we're going to show that is Alon Tarsi. That means the difference is non-zero. Now we claim that difference is this number. It's either this number or the negative of this number, which is not 0, right? Because this is not equal. If the claim is proved, then we finish the proof of this theorem. Okay, now let's prove this. So what I'm going to do, I'm going to so observe that these arcs are not contained in any Euler subdiagrams, because none of these arcs is contained in a directed cycle, right? So every Euler subdiagram of D double prime is contained in this part. Okay, so what I'm going to do, I'm going to use some graph operations to build a one-to-one correspondence between these two sets of Euler subdiagrams. Okay, first let's say what is the graph operations we're going to use. Suppose A and B are arc set, they are disjoint arc set, and use this symmetric difference of A union B. The symmetric difference of A and B. This is, you remove the reverse. Oh, this is definition, but maybe this is more friendly or in the definition. So what is this? This is that I just put the arcs. This is arc set. This is arc set. I put them together. When I put them together, maybe I form some digons. So one arc from A, one arc from B, that form a digon. Then I remove it. Okay, so that is this definition. So for example, if this is a directed cycle and this is the reverse of the directed cycle, take the symmetric difference. Well, it's empty set, right? We put C and C reverse together. They remove the digons. Every edge is contained in a digon. So it's every arc is gone. Okay, like this one, this is A, this is B, and these are the only two common vertices. These vertices are different. Then what is this? We put A and B together. Say put A, just put them together, and then remove digons. Okay. So one observation is that if A, B are both Eulerian digraphs, then the symmetric difference is also Eulerian digraphs, because you put these two together, now each vertex still has in degree equals out degree. If you remove digons, that does not change this fact. In degree still equals out degree. So this is also like this one. This is still a Eulerian subgraph. Okay, so now what I'm going to do, I'm going to take a one-to-one correspondence between these and this. Okay, so you see, I want to prove the difference of this one. Difference is the difference of this one. Okay, so I'm going to build a one-to-one correspondence between these. So take an H from here. So H is a Eulerian subdigraph somewhere here of D double prime. Then I take this directed cycle. What is the cycle? This is this cycle. This cycle is going this way, this way, this way, this way, this way. It's a directed cycle like this. Okay, and take this symmetric difference. You observe that this arc set and the C and H are disjoint. Say this arc is in H. Okay, maybe in H. This is in D prime, but maybe in H. But it is not in C. C is the opposite arc. Right? Even C is in opposite arc. Okay, if you take this symmetric difference, what happens is that, as I said before, it is still a Eulerian subdiagram, because this is Eulerian and this is directed cycle is Eulerian. You put them together, you take the symmetric difference, it's still Eulerian. Now what comes in? This is in C, this is in C. These are going up, this is going this way, that is in C. So their opposite arcs are not in H, so they will show up. They will not be cancelled as digons. Okay, so this will contain this arc and contain this arc. Okay, observe that none of these arcs will be contained in here because either it is not in H or it is in H but then cancelled with the arcs in C, because in arc there's arc going this direction. So if it's in C, it's going to be cancelled. Okay, if it's not in H, then of course it's not there. If it's in H, it's not going to be there anyway. So that means this is actually, it may contain some arcs of C, that means arcs in this direction. That this is a subdigraph of this D. Okay, so it's a Eulerian subdigraph of this D. And the inverse of this, so this is Eulerian subdigraph, but the inverse is also can be defined like this. You take a Eulerian subdigraph, this one, and you take the symmetric difference with the reverse of this directed cycle. That means with this directed cycle, the directed cycle in this direction. Okay, so this is reverse mapping of this one. So this is a one-to-one correspondence between these two sets, two family of Eulerian subdigraphs. And actually, you can say that if C is even, then phi h and h have the same parity, because if C is even, you put them together, they do not change the parity of G. You've removed digons, that does not change the parity of the resulting graph. If it's odd, then phi h and h have different parities. So that means if they keep the parity, then the difference is this minus this. If they change the parity, that is this minus this. So it's negative of this minus this. So the claim is proved. That this means this orientation is Alon Tarsi. And we finished the proof. Okay, so we have proved this theorem that every planar graph G has an Alon Tarsi number at most 5. Now we're going to prove another theorem, which is a joint work with Gruchuk, that is, every planar graph G has a matching M such that if you delete this matching, then the resulting graph is Alon Tarsi number at most 4. Okay, we're going to prove this one. So the proof of this theorem is basically the same as the proof of this theorem. So in proof this theorem, we have this, we give this function, this is the function, and we prove that G has G is the planar graph. It has an orientation D of G minus E such that this out degree is bounded by f v minus 1, and it's Alon Tarsi orientation. This is what we proved. This is a stronger statement. It's more technical statement, but a stronger statement, and we need this stronger technical statement so that we can carry out the induction. And we'll do the same thing. It just the out degree condition is changed a little bit. Okay, so what is the change? Assume M is a matching of G, and we denote by Fm this function. So V1, V2 still gets value 1, and FMV3 is 3 minus dmv. So here f is 3, but this is 3 minus dmv. So dmv is the degree of vertex v in a subgraph M. So M is matching, it's considered as a subgraph. So dmv equals 1 if the vertex is covered by matching edge. It's 0 if it's not covered by any matching edge. Okay, and then the interior vertex has fmv equals 4, so it's 1 less. Okay, because we want to prove this graph is going to be has Alon Tarsi number 4. Okay, at most 4. So then with this definition of this Fm, what are we going to prove? We're going to prove that every planar graph has a matching M. This matching M containing E, such that if you remove the matching, then the resulting graph is F MAT has an orientation. That means it's an Alon Tarsi orientation, okay, and which satisfies the out degree is FMV minus 1 at most. Okay, so the proof is the same, actually the same. The case 1 is exactly the same. There's no change. Just copy it. The case 2 is also the same. Let's go through the just case 2 and say what kind of, it's a small modification, small change. Let's say what is the small change here. We go through the case of the proof of the case 2 for the Nast theorem. So we delete this vertex. We get G prime equals G minus V. By induction, this G prime has a margin M prime containing this H, and G prime minus M prime has an F M prime Alon Tarsi orientation, right? D prime. So D prime is obtained by induction hypothesis, and also the margin M prime is constructed by induction. Okay. So by induction, there is such a margin. Okay, then we extend this to orientation of G minus M prime. So you still delete the edges of M prime, and that means you're going to orient these edges into Vn. The orientation is like this, right? You go this. Okay, so if this is if this orientation, for this orientation the out degree is correct. Okay, this, for example, this one, the out degree is 2. The out degree is 2. That's okay because the out degree is 3 minus dm, the 2 minus dm Vn. But this dm Vn is 0. There's no margin edge. No margin edge carving this vertex. The margin is M prime. M prime is somewhere here. It's a margin of this G prime, which is G minus Vn. Okay, so the out degree of this one is okay. The out degree of this is not changed, and the out degree of this one increased by 1. Because it was a boundary vertex of this plane graph, so the out degree is at most 2. You plus this out degree 1, it's still at most 3. So that's correct. We need every interior vertex has out degree at most 3. So the out degree condition is correct. And if it is Alon Tarsi, then we are done as before. So the only problem is that we need to worry about if that this is not Alon Tarsi. And then we do the same calculation as before. We find this I, we find this cycle, we do the same operation, and we get another orientation. And we proved already this orientation is an Alon Tarsi orientation. Right? This is Alon Tarsi orientation. Okay, but the out degree may go wrong. What could go wrong? The out degree is every vertex is correct except this vertex. Okay, so the out degree is correct except this vertex could be 4. If the out degree of this vertex is 3, is at most 3, then we're done because this is the interior vertex, and that's we just need to make sure this out degree of this vertex is at most 3. And it is 4. It means that originally in this D prime, this vertex has out degree 2, right? 2 plus these 2 new outgoing edges is 4. If it's 2, then that means because by induction hypothesis the out degree should be 2 minus dm prime ui. If this is 2, that means this has to be 0. This has to be 0. If 0 means that this vertex is not covered by this m prime. This is not incident to any edge in m prime. That means I can add this edge, this arc, to m. After adding this to m, okay, then I can remove this. After removing this, then the out degree become correct. The out degree is 1 less, right? So it's 3 now. It's okay. And this is still Alon Tarsi orientation because those arcs are not contained in any Wellerian subdiagram. So you remove it or not remove it does not change the the effect that is Alon Tarsi orientation. So this proves that theorem. Okay, so every planar graph has a matching M such that G minus M has Alon Tarsi number at most 4. Okay, and this result actually is stronger than the result of Cousin and Kister. They proved that every planar graph is one defective, 4 choosable. That means if you take 4 least assignment, then you can remove a matching so that the graph become colorable. So you take a 4 least assignment, the L, then you remove a matching, and that graph become L colorable. This means one defective. That if you do not remove this matching become those edges. The 2 end vertices get the same color. So that's a kind of default edge. Right? Each vertex is adjacent to at most one vertex of the same color as itself. That's one defective. But the consequence of this one is that every planar graph has matching. You can remove it, then this graph is 4 choosable because this graph has Alon Tarsi number at most 4. Therefore, it is 4 choosable. And this matching does not depend on this least, right? And here, the matching depends on the least. So this is a stronger statement. Okay, that's the end. Thank you.